Hi kids, welcome to class. Do this problem. Wow, great job. We have like a 2 kilogram lamp. That's what lamps look like. And they also say 2 kilograms on them. It's on the table. The weight of a 2 kilogram lamp is m times g. 2 kilograms times about 10 meters per second squared, really 9.8. It's about 20 newtons. If we're going to draw a free body diagram for the lamp, Fg downward is 20 newtons. We also can look at the picture. What else is pushing or pulling on the lamp? The table is pushing up with a normal force. And since we know the lamp's in equilibrium, these two forces must add up to 0. The vector sum is 0. So it's also 20 newtons. Got it, Hazel? Yeah, I got it. 20 newtons up, 20 newtons down. They're equal, opposite forces. No, Hazel. Never say that. That is not correct. No good. Never say these two forces are equal and opposite. That's not what we're talking about. They don't have to be equal and opposite. What if I had a super heavy lamp and a super weak broken table? The table could break and the lamp could come crashing through. In that case, Fg would be greater than Fn. What if there's like, I don't know, like an earthquake or something, and the table shakes, and the table gets pushed up, and the lamp goes flying up off the table? That would happen because Fn is greater than Fg. So Fn and Fg are equal in magnitude in this case, but they're not always equal and opposite. So don't say they're equal and opposite. Say Fn and Fg add up to 0. Fnet, I like this sigma for Fnet because it makes you feel smart. Fnet equals 0 newtons. Fnet equals Fn plus Fg. They don't add up, they're not equal and opposite, they add up to 0. Gosh, I get so mad when my babies say that the forces are equal and opposite when they're not, when they just add up to 0. I get so mad, it makes me want to punch my whiteboard. Ready? Ow! I hurt my hands. You can see like a little mark on the hand. No, you can't see it. Yeah, there's like a little. I punched the whiteboard too hard and I hurt my own hand. It's tough when you're strong like me. This is really weird. For some reason, that's what my hand looks like. That's what hands look like. That's not what hands look like. When I punched the whiteboard, I was applying a big force on the whiteboard. But what happened was the whiteboard also applied a force back on me. You can try this with your friends and family at home, I guess. Give them a nice high five. You can give a really soft high five or a really hard high five, like bam. If you give them a really hard high five, you'll both hurt your hands. If you give them a really soft high five, you both will not hurt your hands. There's no way to give someone a high five where you hurt their hands, but they don't hurt your hands. Those forces are equal and opposite. You can say that. This is Newton's third law. We'll learn them in reverse order. This is Newton's third law. You might have heard it said, for every action, there's an equal opposite reaction. That's kind of meaningless. That's kind of silly. Don't think of it that way. For every force, and the force has to be from an object on a second object. Let's say for every force from A on B, there's an equal opposite force. And the force must be the same type of force. That's really important. It must be the same type of force. For every FAB, there exists an equal opposite force, a force from B on A. And those two forces, these forces don't add up to zero. Kind of. They are equal and opposite. FAB is negative FBA. So a few really important rules. They gotta be the same force. If I apply normal force on the whiteboard for my fist, the whiteboard applies a normal force on my fist. And you gotta switch the object and the subject, or some people say you switch the feeler and the dealer of the force. If we're talking about the force from my fist on the whiteboard, the third law paired force is the force from the whiteboard on my fist. So sometimes they're called paired force, sometimes they're called action-reaction forces, sometimes they're called third law forces, but it's the same type, and you switch what's applying the force and what's receiving the force. So the lamp on the table has two forces, gravity and normal force. This is not an example of third law, really important. Don't be confused. This is only for a very specific case, but it's not really a specific case because it always happens to every single force in the whole world. Let's do the common examples really fast. Tension. If I'm trying to pull like a stubborn dog, that's what dogs look like. If I pull really hard with some tension force on the dog will pull back on me with the same force of tension in the opposite direction. That's true. It's true even if the dog is coming with me. If the dog doesn't move at all, I'm applying a large force, and the dog's pulling back with a large force. If the dog's just like a little bit lazy and a little bit slow, and I only give it a little bit of pull, then the dog will only pull back with a very small force too. The same force, obviously, due to the third law. That was tension. How about normal force? We saw the example with the lamp. That's what lamps look like. That's what tables look like. A great drawing. The table is pushing up on the lamp. But third law doesn't say there's also gravity. Third law says if the table pushes up on the lamp pushes down on the table. That makes sense. If it was a really heavy lamp and a really like soft wood table, like balsa wood or something, it might make a dent in the table. If there was like a little ant under the lamp, it might get squished because the lamp's pushing down on the table with exactly the same force the table pushes up on the lamp. Friction too. If you have like a baseball player and they're trying to like slide into home plate or whatever to like score a run, if they're sliding towards the plate, friction from the ground on the player will slow them down. Right? Yeah. If you're sliding across the ground, friction will go against your velocity. It will stop you, slow you sliding. But while that's happening, if there's friction from the dirt on you, there must be friction from you on the dirt. And that's why you kind of like a little cloud of dust. That's cloud. A little cloud of dust. The dust kind of gets pushed forward. There's frictional force from the ground on the player. There's also frictional force from the player on the ground. Kicks up some dust, and then there's a big cloud of dust, and then you have to wait for the cloud to settle, and the umpire goes, safe. When all the dust is clear, you can see what happened in the play. So this is true for tension force, normal force, and frictional force. there's one more important one we talked about. Is it true for gravity? What do you guys think? How is it going to be true for gravity? What do you guys think? Let me say I have a baby sitting on the floor. No, sitting on the earth. That's what babies look like. It's not quite to scale, but it's pretty close. There will be some force from the earth on the baby. Did we break Newton's third law? Will there be no force from the baby on the earth? Tell me what you think. This is going to sound really weird, but if the earth pulls the baby with a force of like, I don't know, like 50 newtons, then the baby pulls up on the earth with the same force. Here's the baby's free body diagram. Actually, no, it's not, because I don't really care about that. But if earth pulls you down with some force, your weight, your body is actually pulling up on the earth with the same force in the opposite direction. It's not normal force. It's not the force from the ground on you pushing you up. You are pulling up on the ground. If you don't believe me, think about, you probably heard about tides, how tides are the moon's gravity. The earth has gravity, the moon has gravity, you have gravity too. It's very small in effect, but it's not a small force. If I weigh 2,000 newtons, I'm pulling up on the earth with the same force, 2,000 newtons. So you don't say it's a small force, but it doesn't really affect things, which we'll talk about next lesson. It doesn't really affect the earth, but everyone on the earth, in fact everything in the universe, is pulling on the earth with a force of gravity, some force of gravity that's not zero. So that's the third law. Good job learning about it. We're all scholars. We did a great job. Okay. We actually kind of already knew this because we know how to walk. This is a very strange example. No, it's not. It's a normal example. No problem. No issue. It's fine. When you're skateboarding, hypothetically, do you take your arm and push yourself forward? That's what hands look like. When you're skateboarding, do you take your arm and push your body to make yourself move? Is that how it works? No, that's not how it works. When you're especially because this is a very weird diagram, when you're skateboarding, you don't push yourself forward. You take your leg and you push the ground backwards. This is a wheel, this is the wheel, this is the foot, and the foot pushes back on the ground. When your foot pushes back on the ground pushes back on you with an equal force. That's how skateboarders move. That's also how humans move, cars move, and planes move too. If there's like a plane, the plane's engines apply a thrust backwards on the air pushes forward on the plane. When a car's wheels are turning, the wheels push back on the ground pushes forward on the wheels. When a person's walking, when you just take a step, when you get up and go to the bathroom, your feet push back on the ground. The ground pushes forward on your feet, and that's how you move forward. That's why you move forward. All motion is really done based on Newton's third law. So that's pretty cool. That's a pretty great example. Good job, me. Thanks. It's a very conceptual problem. So let's look at one conceptual question. Let's say you're in a sailboat and you're stuck in a lake and the sailboat has no engine, it's wind powered, but there's no wind at all. You're stuck in a sailboat, there's no wind, there's no paddles or oars, you can't get anywhere. All you have is a big old fan. That's what fans look like. And it's a battery-powered fan, obviously. So you think, there's no wind hitting my sail. I'll just use the fan and make wind, and then the wind will hit the sail. Is that going to work? If you point your fan at the sail and turn it on, will that be able to move the boat? Use your knowledge of physics. Will a fan pointing at a sail, if the fan's on the boat with the sail, will that move the boat? Tell me now. Will this move the boat? Daisy, what do you think? Well, sails normally move because of wind. The fan basically makes wind. Yeah, that's right, Daisy. So will the sailboat move? Yeah. If we look at the sail, there's a force forward from the wind. That's true, Daisy. But let's look at the don't look at the sail. Okay, look at the sail. Fine. We'll draw the sail. Sail be by diagram. Let's call it F air. That seems right. That seems good and fair to me. Yeah, fair. F air. The force from the air on the sail will push the sail forward. That's true, Daisy. Good job. Thanks, Mitchell Lamb. But there's more to the problem than that. Don't just look at the sail. Look at the fan. What was he talking about? Physics stuff? Yes. Okay, Hazel. No, you're Sage. Okay, Sage. Yes, the sail is pushed forward by the air. That's true. But remind me, Sage, why was the air moving? The fan pushed the air. Oh yeah, the fan pushed the air. So, the fan applies a force on the air. What must be true as a result of Newton's third law? If the fan pushes on the air to make the air go forward into the sail, what else happens? Tell me right now. Wow, great job telling me that if the fan pushes the air pushes back on the fan. So here's the free body diagram for the fan. We don't draw the force from the fan on the air on the fan's free body diagram. You would draw that for the air's free body diagram, but not for the fan's free body diagram. We're drawing the forces on the fan, not from the fan. So since the fan pushes the air forward, the air pushes the fan backward. There's a forward force on the sail from the air, but there's also a backward force on the fan from the air, and they're on the same boat. What does that mean, Hazel? The boat's not going to move at all. Oh, you're right. Yeah, it won't work. Too bad. A sail and a fan won't help the boat move if they're both attached to the same boat. If the fan were off on like an island, that would work fine too. That would be okay. But in this picture, it won't happen. There's another way this would work also. Ooh, I know, Mr. Lamb. Yes, Daisy? They could turn the fan backwards. Oh yeah, they could. If you guys ever go down to like Florida and go on like an alligator scene boat, I don't know. In swampy areas, they use fan boats, which are literally boats with giant fans. But the fan doesn't point at the sail. The fan points backwards. So that fan pushes the air backwards. The air pushes the boat forward. That's good because there's too many roots and stuff in the water, so they could have propeller, it would get like tangled up. So a fan boat uses the third law, like everything else. What a great practice problem. So we all know the third law. Let's do one last thing before the big question that we'll talk about in class. Okay. So let's say this is a very common trope. Someone's like hanging off a cliff, and they're holding someone else hanging off the cliff. And they're saying, "Don't let go, don't let go, oh no." Yeah, this happens in Avengers, happens in Avatar, happens in many things. Let's say they're both 100 kilograms, which is 980 newtons, which is about 1,000. Oh yeah, wait, hang on. Yeah, I'm not 2,000 newtons. I'm like 1,000 newtons. So these are both me. They're about 1,000 newtons. And when I say 1,000 newton person, that means their weight is 1,000 newtons. If I said 100 kilogram person, their mass is 100 kilograms. So these are 1,000 newton or 100 kilogram humans. And they're both hanging one after the other on the cliff. Let's call this person H, and this person BW. No spoilers, but this is H, this is BW. Draw a free body diagram for each one. They both, you can't see my nails. They both have gravity, weight, 100 newtons. That's fine. Since H is hanging on the cliff, there's an upward pull from the cliff. F cliff. But he's also being pulled down by FBW, the force from BW. Since BW is not touching the cliff, there's no force from the cliff on BW. A lot of people will draw like extra forces in their free body diagrams. Don't do that. Only draw a force vector for an object actually pushing or pulling on that object. So there's no force from the cliff on H. There's only a force from H. There's no force from the cliff on BW. There's only a force from H. Sorry for all the confusing letters, but I already wrote it. I'm not going back. I'm going to deal with it. How can we solve these problems? Well, we know that, well, this is too complicated, so look over here. If Fg is 1,000 newtons, Fh must be 1,000 newtons upward. Not because they're equal and opposite. They're not equal and opposite. If BW was too weak and BW let go, they would not be the same. They would not be equal and opposite. They add up to 0 because BW is in equilibrium. Since we know FH is 1,000 newtons, this is the force from H on BW. If we know this is 1,000 newtons upward, this force, the force on H from BW, must be 1,000 newtons downward. We also know Fg, 1,000 newtons downward because of H's weight. Thus, Fc must be 2,000 newtons upward to restore equilibrium, not because equal and opposite, because these three forces, 2,000 up, 1,000 down, 1,000 down, add up to 0. So on person H, their weight is 1,000 down. The pull from the second person on the first person is 1,000 down. The force upward will be twice as much, 2,000. Pretty straightforward numbers. The problem makes sense pretty easily, but ask me if you're not sure. It's really important. Don't say that the second person's weight is felt by the first person. Don't say that these forces are equal and opposite. Don't say the force is like transferred or anything like that. since the first person applies a force upward on the second second person applies an equal opposite force downward on the first person. So that's an idea. Make sure you ask me in class if you understand, because it's really important. And one last really important thing. Newton's third law is true, but how do things move? It doesn't make any sense. I'm so confused. My brain's broken. Let's say we have like a horse. This is what horses look like, in case you didn't know. A perfect horse, drawn perfectly. Let's say it's pulling a big stagecoach. That's what stagecoaches look like. It's a oxymoron. Well, there's some force from the horse on the stagecoach. But due to the third law, there must be an equal force from the stagecoach on the horse. That's true. But if that's true, how can the horse move at all? How can the horse move at all? It's a tough question. If you know, tell me. How can the horse move if every force from the horse on the stagecoach results in equal force from the stagecoach on the horse? If you're not sure, I'll tell you in class.